In this video, I'll be showing several examples where you're using the main kinematic equations to solve problems where you have motion with a constant acceleration. The three main kinematic equations are listed on this slide. The first one gives us velocity as a function of time. So if we want to find the instantaneous velocity, the velocity at a specific instant in time, this equation allows us to find it. The second equation allows us to find position as a function of time. So what is the position at time t? And the third equation actually comes from combining the first and second equations. If you solve the first equation for t and plug it into the second equation, this actually gives us the third equation, which is velocity as a function of position. What is the velocity when the object is at position x? What you're really doing is you're finding what is the velocity at the time when the object is at position x. In these equations, the notation v sub 0 stands for the velocity when t equals 0, and the x sub 0 stands for the position when t equals 0. So that subscript 0 notation is often used to stand for the initial conditions. What is the initial velocity of the object, or what is the initial position of the object? What is the position or the velocity when t equals 0? So in this first problem, we have an electron in a cathode ray tube, and it enters a region where it accelerates uniformly, and it goes from a speed of 30,000 meters per second to a speed of 5 million meters per second in a very short distance, 0.02 meters, 2 centimeters. Again, these speeds might seem extremely large, and they are, but this is an electron. An electron is extremely light, and so it's very easy to make it have this large of an increase in speed in just a short distance. So the method that I recommend for trying to solve these problems, any type of problem that you have with motion with a constant acceleration, is to first list out all the different variables. And you set up a table. And so the different things you would have in the table would be x sub 0, the initial position, or x, or the initial velocity v sub 0, or the velocity at time t, v, or the acceleration, or the time. And in this problem, the particle is starting at a position of 0 meters, and a little bit later, it's at a position of 0.02 meters. This electron is starting with a velocity of 30,000 meters per second, and a little bit later, it has a velocity of 5 times 10 to the 6th meters per second, 5 million meters per second. And in this problem, the first thing we're asked to do is find the acceleration. And in the second part of the problem, we're asked to find at what time does it reach the end of the 0.02 meters. So for this, as you're trying to figure out what equation to use, it's good to just try and compare the quantities that you have, the x0, x, v0, v, a, t, with the equations. And if we look, all of the equations have acceleration in them, but two of the equations have time in them also, and we don't know the time. The equation that doesn't have time was the third equation that I had written that related the velocity to the position. And if we look at this equation, we know what this velocity is, we know what this initial velocity is, we know what these ending and starting positions are, and so the only thing that we have left to do is to solve for the acceleration. And so we can plug our values in and solve this. So our ending velocity is 5 times 10 to the 6th meters per second, and it's that velocity squared, equals the initial velocity of 30,000 meters per second squared, plus 2 times the unknown acceleration a times the displacement of 0.02 meters minus 0 meters. And so if we square out these quantities, 5 times 10 to the 6th squared, that's 2.5 times 10 to the 13th. And this equals 9 times 10 to the 8th Again, this is meters squared per second squared, meters squared per second squared, plus 2 times the acceleration times 0.02 meters. And so we would subtract the 9 times 10 to the 8th over to the other side, divide by the quantity 2 times 0.02, and this would give an acceleration of 6.2498 times 10 to the 14th meters per second squared. Again, this might seem like a very large value, but this is an electron. An electron has a very small mass, so it's easy to give an electron such a large acceleration. Part B, how much time does it take for the electron to travel the 0.02 meters? Well, now we know what the initial velocity is, we know what the final velocity is, and we know what the acceleration is. So the easiest way to solve this would be to use the equation for velocity as a function of time, v equals v0 plus at. We could use the second equation also for position as a function of time. That one would be a little bit more complicated. We'd have a quadratic that we have to solve. But this one we can solve very easily. So again, we'll often try and choose the method that's going to be the easiest. So we have 5 times 10 to the 6th meters per second equals 30,000 meters per second, plus the acceleration that we just found, 6.2498 times 10 to the 14th meters per second squared, times the unknown time t. So all we're left with is solving for t. So again, we subtract 30,000 over to the left-hand side. We divide by the acceleration, and this gives us a time of 7.9523 times 10 to the negative 9 seconds. This is 7.9 nanoseconds. Again, it's an extremely short time, so we should always check to see, does this make sense? If we have an electron and it's traveling 2 centimeters, so not a very large distance, and it's traveling at 5 million meters per second at the end. So again, it's going from 30,000 to 5 million meters per second, so it's moving extremely quickly. It's going to travel the 0.02 meters in a very short period of time. So again, this answer does seem like it might make sense. This next problem, we have another very basic problem. We have a car starting from rest and reaching a speed of 7.5 meters per second in 4.2 seconds. And we're going to try and calculate the acceleration and how far it travels. And so again, make a list of all the different variables. And again, just like I did in the last problem, I'm going to let the object start at a position of 0. We're not interested in what its position is. We're really interested in how far it travels, or how far is it from its starting point, which is really its displacement. So in this problem, just like the last problem, I'm going to let the initial position be 0 meters. And this is starting from rest. So again, that's a key phrase in there that means that it starts with a velocity of 0 meters per second. And this is saying that it has a velocity of 7.5 meters per second when the time is 4.2 seconds. So we're going to try and find the acceleration. So again, we know the initial velocity, we know the final velocity, we know the time. So it makes sense to look at the equation that relates velocity and time. So we have 7.5 meters per second equals 0 meters per second plus the acceleration times 4.2 seconds. This gives us an acceleration of 1.786 meters per second squared. So now that I know that value, I can plug it in over here into my table. And so now when I go to solve part B, how far will it have traveled in that time? Again, I could use either of the other two equations because I know everything except the final position. So I could use velocity as a function of position, or I could use position as a function of time. Again, I think for most people it makes more sense to use the equation for position as a function of time, so that's what I will do. So in this we have that the final position, which we're looking for, equals the initial position of 0 meters plus the initial velocity of 0 meters per second times 4.2 seconds plus 1/2 times 1.786 meters per second squared times 4.2 squared. So 0 times anything is 0. So this gives us 15.75 meters. So this car traveled 15.75 meters in those 4.2 seconds. This next problem is a little bit longer. This is not just a simple one-step problem. So in this problem, we have an automobile that accelerates from rest with an acceleration of 2 meters per second squared for 20 seconds. And then it holds its speed constant for 20 seconds. And then it has an acceleration of -3 meters per second squared up until it stops. And we're going to try and find the total distance traveled. And so what we're going to do is we're going to break this up into 3 parts. The first part, the object is accelerating. And so it goes from rest, and it accelerates at 2 meters per second squared for 20 seconds. So I'm going to let the initial position be 0. The initial velocity is 0 meters per second. The acceleration is 2 meters per second squared. And what we're trying to do is we're going to need to figure out how far does it travel in 20 seconds. Something else that we're going to need is we're also going to need to figure out how fast is it traveling at the end of those 20 seconds. Because both of those things are going to be important for the next part. In the next part, we need to know how far it has already traveled, and we need to know how fast it's going so it can then hold that speed constant. So first, to find how far it traveled, we'll find position as a function of time. So our initial position is 0. The initial velocity was 0 meters per second times 20 seconds plus 1/2 times 2 meters per second squared times 20 squared. And this gives that the car travels 400 meters in that first segment. To find the velocity that it has at the end of that first segment, we can use velocity as a function of time. So we have that the velocity equals the initial velocity of 0 meters per second plus 2 meters per second squared times 20 seconds. So it's going to be going 40 meters per second at the end of those 20 seconds. And then for this next piece, it travels at a constant speed for 20 seconds. And so if I just figure out how far it travels during this piece, I could go through and I could do that by doing the 40 meters per second times 20 seconds, and that would give me 800 meters. Or if I wanted to actually, use what I've been doing, I could say that it's now starting at 400 meters. So then I could figure out exactly where I'm at. So instead of saying that it's 400 meters for the first part and then 800 meters for the second part, I can just include all this in. I can have that starting position be 400 meters. And so then I'm going to try and find this later position. The initial velocity is the 40 meters per second. The final velocity is still 40 meters per second. And since it's traveling at a constant velocity, that means that there's no acceleration. And my time is 20 seconds. So again, I can look at position as a function of time. So it's going to be 400 meters for the starting position plus 40 meters per second times 20 seconds plus 0 because there's no acceleration. So this is going to give me my 1200 meters. It traveled 800 meters and it was already 400 meters along, so now it has traveled a total distance of 1,200 meters. Then for this final part, we have it starting at a position of 1,200 meters. The initial velocity is the 40 meters per second. And this has an acceleration of -3 meters per second squared. Again, that was given up at the beginning of the problem, so we have an acceleration of 3 meters per second squared. And we're not told how much time this takes. And so, again, there's a couple of methods that we could do. We could do this in 2 steps. We know that it's going to reach a final velocity of 0 meters per second. And so I could figure out how much time it takes to reach that velocity and then plug it into the position as a function of time equation. Or if I want to do it in 1 step, I could just use the equation for velocity as a function of position. Either method is equally valid. Either method is just as correct. A lot of people find using the 2 equations for position and velocity as a function of time to be a little bit easier. So even though it's 2 steps, they prefer to do it. That's perfectly fine. I'm going to use the equation where I can do it in 1 step. So I can look at the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement, x minus x0. So I have a final velocity of 0 meters per second. That equals my initial velocity of 40 meters per second. There's that quantity squared, plus 2 times my acceleration of -3 meters per second squared, times my final position x minus my initial position of 1,200 meters. And so if I do this, I'm going to square the 40. I can then take it over to the left-hand side of the equal sign. I divide by -6. And then I'm going to add 1,200 to both sides. And so this is going to give me a final position of 1,466.667 meters. And kind of just looking at what we had 3 pieces. So in the first piece, it traveled a distance of 400 meters. The velocity was 0 on this side. The velocity ended up being 40 meters per second on this side. And then it traveled at a constant 40 meters per second for 800 meters. So at that point, it was 1,200 meters. And then for this last part, it went from 40 meters per second down to 0 meters per second. It had an acceleration of -3 meters per second squared. And for this segment, it traveled 266.67 meters. And again, I would just go through and I would add those pieces together. So some people may have found it easier just to look at each piece separately. Kind of start the position at 0 for each piece, find how far it travels during each piece, and then go through and figure out what the total distance traveled is. Again, either method would be okay. This method is just a little bit more complete and it includes all the positions. It's a little bit more formal method. For this next problem, we have a helicopter descending from a height of 600 meters with a uniform upward acceleration. So I'm going to look at this helicopter, and it's going down 600 meters. We don't know what this initial downward velocity is, but we do know that the velocity is 0 at the bottom. And we do know that it takes 300 seconds for this to happen. So again, just like everything, I'm going to list my initial position. So I could use y since these are vertical positions, or I could just say that this is x equals 0 and this starting position is 600 meters and my x-axis is just in the vertical direction. So I'm letting it start at a position of 600 meters. it's ending at a position of 0 meters. The initial velocity I don't know. I do know that the final velocity is 0 meters per second. I don't know what the acceleration is, and I do know that the time is 5 minutes, which is 300 seconds. And so I start to compare this to my equations, and I realize that there's a problem. All of the equations have this initial velocity v sub 0 in them, and they also all have that acceleration in them. So there's not one equation that we have that there's only one thing that we don't know. For this one, we're going to have to come up with another equation. We're going to have to use a little bit of substitution to be able to figure this out. And so the way that we can do this, in some classes this is presented as a fourth kinematic equation. I find it easier just to come up with it when you need it. I can look at that first equation, v equals v0 plus acceleration times the time, and I could solve that for the initial velocity in terms of everything else. That initial velocity is v minus at. And then I could look at the position as a function of time equation. And I could take this initial velocity in terms of the final velocity and the acceleration, and I could substitute that in. So that's going to give me x equals x sub 0 plus the quantity v minus at times t plus 1/2 a t squared. Or simplifying that a little bit, multiplying that middle term by t, I have x equals x0 plus, this is going to be vt minus a t squared, so I distributed the t to both of those terms, plus 1/2 a t squared. And so I can combine the negative at squared plus 1/2 at squared. So this is negative 1 at squared plus 1/2 at squared gives negative 1/2 at squared. So I have that x equals x sub 0 plus the final velocity times t minus 1/2 a t squared. And the reason that I don't usually recommend just knowing this as a fourth equation is very easy to get confused with the equation for position as a function of time with the initial velocity in it. The two differences are one has initial velocity, one has final velocity, and then one has a positive 1/2 at squared, one has a negative 1/2 at squared. I think it's usually too easy to confuse the two, so whenever I need this equation with final velocity in it, I usually prefer to just come up with it on my own. And so then I would go through and I could plug in the different values. I have 0 meters equals 600 meters plus the final velocity of 0 meters per second times 300 seconds minus 1/2 a times 300 seconds, quantity squared. And so again, 0 times 300 is still 0. And so I take the 1/2 a times 300 squared over to the left-hand side of the equal sign. I multiply both sides by 2, divide both sides by 300 squared, and this gives me that the acceleration is positive 0.01333 meters per second squared. I'm going to check to see if this answer agrees with what we were told. We were told that it has a uniform acceleration that's directed upwards, and so our acceleration should be positive. In this, the positions were increasing as we moved upwards, so we were saying that upward was the positive direction. Then, to figure out the initial vertical velocity, again, we now know this acceleration. So we know the initial position, the final velocity, the acceleration, the time. So we can use either of the two equations that we haven't used. But again, I said, if possible, the equation for velocity as a function of time usually tends to be the easiest one to use. So I can use that one here. So I have that the final velocity is 0 meters per second. That equals the unknown initial velocity v sub 0 plus the acceleration positive 0.01333 meters per second squared times 300 seconds. And so if I solve that for the initial velocity, I get negative 4 meters per second. And again, to check to see if this agrees with what we were told that it was initially moving downward, so that velocity should be negative. Okay. This next problem is a very common type of problem where we have two objects that are moving. And we're going to try and figure out when the one object catches the other object. So here we have a speeder passing a police car. So if I look at the speeding car, I can write all my variables for it. So we're told that a speeder passes a parked police car traveling at 45 meters per second. So this car is traveling at 45 meters per second. The police car starts from rest with a uniform acceleration of 2.44 meters per second squared. And we're assuming that the speeder continues at a constant velocity, doesn't try and slam on the brakes to slow down because the cop is after him. How long does it take for the police car to catch the speeder, and how far does the speeder get? So in this, we're letting, when the speeder passes the police car, we're letting that be the starting position. So we can let that initial position be 0 meters. Because the speeder continues at a constant velocity, he has an acceleration of 0 meters per second squared. If I look at the police car, he's also starting at a position of 0 meters. He's starting from rest, so he has an initial velocity of 0 meters per second. And he has an acceleration of 2.44 meters per second squared. And so we're trying to figure out how long does it take for the police car to catch the speeder. For the police car to catch the speeder, that means that the position of the speeder and the position of the police car have to be the same. He's caught when they're at the same position. It has nothing to do with the two of them having the same velocity. The police car catches the speeder when he is at the same position as the speeder. So we're going to look at the equations for position as a function of time. But for this, we're going to have to do this for both the speeding car and the police car. And so for the speeding car, again, we're going to have x sub 0 plus v sub 0 t plus 1/2 times the acceleration times the time squared. So this is going to be 0 plus 45 meters per second times t plus 0. There's no acceleration, so that last term drops out. For the police car, again we have the initial position plus the initial velocity times the time plus 1/2 the acceleration times the time squared. So now the position of the police car is going to equal 0 plus, this has an initial velocity of 0, so again that term goes away, plus 1/2 times 2.44 times t squared. So we said that the speeder is caught by the police car when they're at the same position. So I set these two things equal to each other. So I have 45 meters per second times t, that's the position of the speeder, equals 1/2 times 2.44 times t squared. Now this problem, because they're both starting at x equals 0, works out a little bit easier. Um, we can divide both sides by t, and it simplifies the equation a little bit. We have 45 equals 1.22t, or it gives us a time of 36.885 seconds. And then to find the position, how far does the speeder get, we're going to plug that time back into the position of the speeder. And actually we could plug it back into the position of the speeder or the position of the policeman, because at this time they're both at the same position. But to figure out how far he got, I'll plug it back into the equation for the position of the speeder, because that one's a little bit easier. That's going to be 45 meters per second times 36.885 seconds. So that gets that the speeder has traveled 1,659.84 meters. So he goes about 1.6 or 1.66 kilometers. Again, it's going to take a little while for this police car to catch up with the speeder, because the speeder was going pretty fast. 45 meters per second is over 90 miles per hour. The last problem that I have is a similar type of question, except the two objects do not start in the same spot. So to help out, I'm going to draw this situation. And so we have two particles both moving in the same direction along the x-axis. We have particle A starting at a position of 2 meters. We have particle B that's starting at a position of 1.5 meters. So here's object A, and here is object B. But they're both traveling to the right. We're told that object A, again, starts at a position of 2 meters, and it has an initial velocity of 7.5 meters per second, and it has an acceleration of 2.7 meters per second squared. Particle B starts behind it at 1.5 meters. It's starting at 2.2 meters per second, but it has a larger acceleration. The acceleration of particle B is positive 5.1 meters per second squared. So again, in a similar method to what I did before, I'm going to look at particle A. So I'll look at its starting position, but now that's not 0, it's 2 meters. I don't know what the final position is. I do know that it starts with a velocity of 7.5 meters per second. And I do know that it has an acceleration of 2.7 meters per second squared. For object B, I know that it's starting at a position of 1.5 meters, and I know that it has an initial velocity of 2.2 meters per second. And I know that it has an acceleration of 5.1 meters per second squared. So again, I'm going to look for when these two are at the same position. So I'm going to start by finding the equation for the position of object A as a function of time. So that's going to be the initial position of 2 meters plus the initial velocity, 7.5 meters per second, times t, the unknown time, plus 1/2 times the acceleration of 2.7 meters per second squared times t squared. Again, I highly recommend that you have the equations written out next to you as you're trying to work through these, so that way you can look at them as you're trying to plug the values in. This second equation is for the position of object B. So it starts at a position of 1.5 meters. It's starting at 2.2 meters per second times t plus 1/2 times its acceleration of 5.1 meters per second squared times t squared. And again, we're going to set those two equations equal to each other. But we can see already that this is not going to be as simple as the last one. And I'm going to drop the units for this just to make things a little bit simpler. So I'm going to have 2 plus 7.5t plus 1/2 times 2.7 times t squared is going to equal 1.5 plus 2.2t plus 1/2 times 5.1 times the quantity t squared. And so here I don't have any terms that cancel out. I can't divide both sides by a t. And so this is going to be a quadratic equation that I'm going to have to solve. So the first thing that I'm going to need to do is just kind of subtract everything over. So 1/2 times 5.1 minus 1/2 times 2.7, that gives me 1.2 t squared. And then 2.2t minus 7.5t, that gives me negative 5.3t. And then 1.5 minus 2, that gives me negative 0.5. And that equals 0. So again, all I did was I combined like terms. I got everything over to one side of the equal sign. For the equation that I have, I took everything from the left-hand side of the equal sign and I moved it over to the right-hand side of the equal sign. And then you have a quadratic that you're going to solve. There's several methods that you could do. You could use the quadratic formula where 1.2 is the a in the quadratic formula. In the quadratic formula, b would be negative 5.3 and c would be negative 0.5. And again, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac. It's that whole quantity divided by 2a. So you see with this quadratic formula, you're going to get two different solutions. Another method of solving this would be to just graph this function and find where it crosses the horizontal axis. So I could graph 1.2x squared minus 5.3x minus 0.5, and then I try and solve for the solutions when, what values of x make that graph 0. Or you may have a calculator with a built-in quadratic formula solving program, or you may have a TI Inspire CAS, which has a solve feature. Whichever method you use, you're going to go through and you're going to solve for your different values of time. I'm interested in the answer because at this point we're done with the physics. At that point it's a math problem. But when you do this, you're going to get either t equals negative 0.0924, or you get that t equals 4.5091 seconds. And so we have to figure out which of those we want. The negative 0.0924 seconds, that happens before the objects even started. It happens almost 1/10 of a second before they started. So the one that we're interested in is 4.509 seconds. So again, we could then go through and find what position they're at. We could figure out what velocity they have. We could use that time, and we could use the equation for velocity as a function of time to figure out what the two velocities of those objects are. But this problem was only asking us to solve for the time. And again, this is a little bit more complicated problem, but it's still the same idea. You still go through and do the same thing. You set up your position x0, x, v0, v, a, t. You set up a table with all those values, and you go through and you try and figure things out. This one just had the extra wrinkle that you had to understand that the one object passing the other object meant that they were at the same position. So again, the only way that you get good at doing these problems with motion with a constant acceleration is through practice. So I encourage you to do a lot more practice, and hopefully as you practice, you'll get better and better, and you'll be able to solve them faster and faster.